To mine heat anywhere in the world economically, we need to drill wells to reach even higher temperatures, in some locations deep into hard rock formations. Aside from the associated temperature challenges, drilling into basement rock poses significant technological challenges. Many in oil and gas are looking to existing contemporary drilling technologies, like PDC drill bits, to help solve geothermal drilling challenges. But there are scientists developing new ways of approaching the challenge of drilling in extreme conditions, and these largely non-mechanical methods of drilling may provide a step change in the way we approach drilling for geothermal in the future. So, what are these new drilling methods? Where are they in their testing and development? And how could we integrate these new technologies into existing oil and gas operations? Let's explore.
Hello and welcome to the Future of Drilling for Deep Geothermal panel at Pivot 2021. I hope you all watched and enjoyed the deep and super hot geothermal panel that just wrapped up. We'll be exploring how exactly we can drill those wells in this panel. My name is Jody Robbins, and I am a senior geothermal engineer at NREL, where I've been focusing on geothermal for the past 2+ years. Previous to that, I spent 22 years in oil and gas, working for a variety of companies, from a super major down to a private equity-backed company that I helped found. Most of my time in the industry was spent in drilling and operations, which is why I am so interested in today's discussion. For your viewing pleasure, our 4 panelists are from 4 different companies or organizations that are pursuing novel drilling technologies that aim to facilitate faster, deeper, and cheaper drilling of geothermal wells, especially in deep and hot environments. With that, let's get to our panel. I'm going to give them each a few minutes to introduce themselves. First up is Carlos Araque, co-founder and CEO of Quaise Incorporated.
Thank you, Jody. Hello, everybody, and thanks for the opportunity to be here. So I come from the oil and gas industry. I spent 15 years in Schlumberger, and all of that time was really looking at subsurface technologies, product development. Back in 2017, I decided to change courses a little bit and explore the energy transition more closely. So I founded Quaise based on work going on at MIT. At Quaise, we're trying to drill deeper and hotter than ever before possible. We're talking about 20 kilometers and 500 degrees C. That truly makes geothermal global. It brings it everywhere in the world at the power densities of fossil fuels. It makes geothermal into a terawatt source. Jody, back to you.
Thank you. Next, let's hear from Igor Kochich, CEO at GA Drilling.
Yeah, thank you, Jody, for this opportunity to be here today. I'm Igor, and my background is technology. I'm coming from the electrical engineering industry, and therefore also my focus also in our work is to develop something that could revolutionize and change the drilling industry. Our main motivation when we found the company 10 years ago was first of all to make the fundamental research around the different approaches that can revolutionize and change it. So we tested also the thermal and also mechanical technologies, and as a result of this several years work, we came out with the plasma as a way that we can drill much faster and cheaper as it is today. And our focus is also to really tap the potential of the geothermal that is currently hidden in the deep depths and the high pressures, high temperatures.
Great, thank you, Igor, welcome. Next, we'll go to Mark Russell, the CEO of Hypersciences.
Thanks, Jody. I'm Mark Russell, founder of Hypersciences. My background actually is aerospace engineering. I led the crew capsule development for the vehicle that Jeff Bezos just flew in this week. What we do at Hypersciences is we merge hypersonic industrial together. So we fly things about the size of a bottle cap at hypersonic speeds underground, allowing the drill bit to drill about 10 times faster in hard, deep, and high temperature rock. So we're funded by Shell and major energy and mining companies to develop the world's fastest, lowest cost drill. You drill exactly like you normally drill, except you drill a lot faster, pushing these projectiles down through a central line. We're in field trials, and so we're excited to use this as an exploration drill as well as a large, deep, hot geothermal anywhere type drill in the future. So again, Mark Russell, and thanks very much for having me for Hypersciences.
Thanks, Mark. And finally, we have Naveen Vilmurugan, the Scientific and Technical Manager at Orchid.
Thanks, Jerry. It's a pleasure to be at Pivot 2021 and among other experts of this panel. Yeah, my name is Naveen Velmurugan, actually, and I'm an odd man out of the panel. So I come from a very academic background. I'm a drilling engineer by background, and I have a PhD in mathematics and control from École de Mines in France. And the project Orchid, we are actually funded by the European Union under Horizon 2020 program. We received about 4 million euros in grant for a period of about 3 years. The goal is to test a prototype of a drilling technology that combines two mature technologies, that is high pressure water jetting and percussion drilling. This project is led by Armin, Main Paritech in France, coordinated by Dr. Laurent Gerbeau and Professor Hedi Salami. The consortium includes about 6 different partners from 5 different countries. So more about the technology and what we do as we go along. Back to you, Jody.
Thank you, Naveen. Welcome. Yeah, I think before we can really get started here, let's hear a little bit about each of your organizations and a little bit more about your drilling technology that you're working on. So let's again start with Carlos.
All right, so Quaise is developing millimeter wave drilling systems. They're meant truly for basement geology. You know, when we're talking about a large global geothermal, we're talking about basement geothermal. There's going to be a lot of growth in geothermal with sedimentary basins, but we ultimately believe you have to drill in the basement to realize the full potential. So we think millimeter wave drilling is a fit for purpose technology for the basement. Our basic idea is drill to basement rock conventionally, can be any of the technologies, rotary, hammer, any conventional or novel technologies. And when once you're in basement, you're in a very different geological setting. So in some ways you can do things differently. We switch over from a liquid mud-based system to a dry-based system, an air-based system. And we simply convey 2 things into the hole. You know, the in-hole complexity is minimum. So we gotta keep it that way because putting things in the hole is hard and it leads to reliability issues. So at the surface, we have a gyrotron. That's a microwave source. We beam the energy through the pipe. The pipe looks just like oil pipe. It's 4.5 or 5.5 inch tubing. And together with this energy, we push a stream of gas. We circulate in the same way that you would do direct air drilling, direct circulation air drilling. And at the bottom of the well, you basically vaporize the rock and convey the particles back up to the surface. We think the real breakthrough is in the transmission line, right? As you drill deeper and hotter, the difficulty is going to be in getting the energy down to the rock from the surface. And I think with our transmission line, which looks exactly just like oil pipe, or it is oil pipe, we're going to be able to do that. We're early in technology development. We've completed a lot of lab scale up as far as we can practically go in the lab, and we're now facing the next 3 years into field trials. We're going to be working with a large drilling company to integrate our drilling systems into theirs and actually go and do this in the field over the next 3 years. Back to you, Jody.
Nice. Yeah, that sounds great. Let's go to Igor next.
Yeah, so our company, GA Drilling, stands for Geothermal Anywhere since the beginning. We are focusing on the development and now testing the system that is able to utilize the very hot stream of material. In our case, is the fluid that we can use against any kind of rock. Even our focus is totally currently for the hard rocks. Because always when you are going deeper to the several kilometers depth, there is a high pressure, high temperature environment. And what is our way, how we are drilling, we are trying, as a strategy, we are trying to utilize as much as possible from conventional systems. It means that utilize as much as possible of the equipment, rigs, power generators, and so on. But what we are changing is this core of the system. In our case, it's called like plasma drilling tool or plasma bead, where we are destroying the rock, not by melting or evaporating. In our case, we then move to the destruction of the rock by thermal stressing. And it creates a very similar process thermally, how it is in a mechanical drilling. So we are creating small cuttings of the rock that basically they look very similarly like a normal cuttings from mechanical drilling. Only what is advantage also here is their size is quite standard in a very small size, and the removal of the materials is also in the normal fluid management system. So here is our also strategy regarding the next months and 2-3 years. Is our full focus to now integrate it. That's what we are doing last 3-4 years, very intensively working with equipment producers regarding the rigs, regarding the transfer lines. When we are using, for example, as a main energy is the electrical energy on the useful voltages that you can easily transfer through several kilometers. And now in next 2-3 years, the next plan is to work closely with the drilling company and the operator that we can bring step by step the technology to the pilot, to the field, and being able to drill first sections of the deep wells. So that's target.
Okay, all right. Mark, do you want to tell us a little bit more about Hyperscience?
Yeah, sure. I think first I applaud everybody in the panel for coming in and showing the world brand new technology. Old-fashioned drilling uses rotary technology that is slowly tearing and grinding away the rock. All the gentlemen on the panel here today are doing amazing things, trying to change fundamentally, bringing energy to the bottom of a hole. What we do at Hypersciences is we use simple chemical energy to fire projectiles that are made out of biodegradable plastic and concrete at supersonic speeds and hypersonic speeds just in front of a rotating bit. So our bottom hole assembly brings all the energy, compressed air, and simple things like biodiesel into a bottom hole assembly where they're combined and using simple chemistry, firing a projectile every 10 seconds in front of a rotating bit, breaking about 90% of the rock in front of that bit. So the bit only does the final cleanup and gets you that perfect hole that you want. But again, pulverizing the rock and bring it up just as normal drill cuttings. So the fundamental difference is we bring energy at a dynamic pressure that's 10 to 100 strength, 100 times the strength of the compressive strength of the rock, thereby pulverizing both the rock and the projectile in a fashion known as hydroelastic behavior. Both the projectile and the rock see each other as a fluid when they hit at those speeds. So everything breaks up. We're temperature and rock strength and depth independent. And we're in field trials with majors. So what we've done is created an incremental, what we call a hyper incremental approach, much like what we did in aerospace with Jeff Bezos, is slowly, gradually, ferociously. We're doing a small projectiles every few seconds. We're actually using them for tunnel boring today, exploration drilling to 1,000 meters, and then growing the system into what we think will be the way to create major holes for geothermal anywhere that are production and case while you drill. As you drill in this manner, you can actually 3D print a casing at the same time. So not only are you solving the compressive breaking of rock, but you're also being able to bring in materials that form the hole as you're doing it. And we're excited. We're in field trials and it works really, really well. The deeper and higher pressure turns out actually improves the performance.
Thank you, Mark. Yeah, that sounds really interesting, especially the casing, printing casing while you drill is kind of stuck out there as something that I hadn't heard before. Naveen, why don't you tell us a little bit more about the Orchid project?
Perfect, for sure. Yeah, I would say that we are slightly early stage as compared to rest of the technologies that we discussed in the panel. So the goal of this particular project is to increase the rate of penetration in hard rocks by at least 3 times. So from studies, we know that the ROP is about 1 to 2 meters per hour for now, but we want to go up to, let's say, 4 to 10 meters per hour for hard rocks and especially in basements for deep geothermal systems. The way we would like to do that is to combine two different well-established mature technologies. The first one is the percussion drilling, and the other one is high-pressure water jetting process. So we would like to create a prototype over a period of 3 years that could combine these two technology into one single, let's say, an equipment. And we would like to deliver high-pressure water jets through one of the nozzles of the drill bit so that we can create some groove through a slotting process in the downhole conditions. What would then happen is it would release some stress or the in-situ stress around that particular rock surface, creating a free surface. And then we go on and do purposive drilling using the down the hole hammer technologies, thereby increasing the ROP. And interestingly, we are aiming to produce this ultra high pressure water jets downhole using intensifier that would translate the drilling vibrations into fluid pressure into a chamber. So that's basically the goal of Orchid project. And we have several partners working on different aspects of this whole process to put together. And yeah, perhaps we can discuss further during the discussion. Yes, back to you, Jody.
Yeah, but why don't you tell us about your partners?
Okay, sure. So as I said, the project is led by Armin Main Biotech. What we have here in France is a laboratory set up to emulate downhole conditions of about 5 kilometers. We can provide in-situ stress to the rock sample for about 100 megapascals and a different temperature range up to 350 degrees Celsius. We are setting up experiments to test the high pressure water jetting process for creating these grooves in different rock candidates. We have chosen about 6 different rock samples that could act as candidates of, let's say, various geothermal lithological surfaces around the globe. The other partner is Imperial College London in UK. They are an expert in studying the jetting process of the impact of the jetting process on micron mesostructure of the rock samples. They help understand the rock cutting process due to ultra high pressure water jets. And these simulations are done for the normal conditions. We have a partner from Norway who is Sintef. They are an expert in carrying out simulation studies of the bit-rock interaction due to the hammering process and the resulting dynamics in the drill string. They also study samples of water-based mud mixed with some graphene or graphene oxide nanoparticles to understand the fluid loss mitigation through natural fractures, as well as the impact of those nanoparticles on the jetting process. We have another partner in France, which is Drillstar Industries. They are an equipment manufacturer, especially for geothermal industry. They manufacture down the hole hammer technology and hammer bits. They are an industrial partner who will provide us with the technology to develop the prototype. They will also be an immediate user and facilitator of this technology through field trials. We also have a partner from China, China University of Petroleum in East China. They are an expert in designing these intensifiers, which are the downhole tools that convert the drill string vibrations into fluid pressure. So we aim to achieve up to 150 or 200 megapascals of fluid pressure to create this ultra high pressure jets. Last but not least, we have University of Piraeus Research Center in Greece. They study the environmental, social sustainability aspect of this particular project. Some of the tasks include social impact assessment and energy security implications of the technology developed in Orchid. So that's a brief about the partners involved in this particular project. And yeah, as I said, the project is going to go on for 3 years. We just commenced this project January 2021. So yeah.
Okay. Thank you, Naveen. We're already getting some really interesting questions from the audience, so I'm going to start mixing those in now. And I think I'm going to try to stay a little bit more technical at the beginning and then get more general as we go along. So first up is a question for Mark. And that is, how is the design of explosives adjusted for the high temperatures? And how are the explosives transported downhole?
Okay, so you can hear me okay, Jody?
Yes.
Okay, so what we do is we use compressed air and the oxygen that's in normally compressed air as the oxidizer. The fuel we bring down with the projectile, and it's basically again a biodiesel or diesel component. So they're mixed at the point of use where you want the energy. So you just have these floating discrete particles of projectile and material that then get mixed at the bottom of the hole in your bottom hole assembly. So if from a safety standpoint, we've worked with Shell and other majors, this really operates just like a conventional drilling system. You're not bringing pre-mixed oxidizer and fuel explosives like in a perforation charge system. You're actually mixing them at the bottom of the hole using the exact same systems that we currently use for drilling, natural gas or fuel, and then compressed air.
Okay. Oh, sorry, getting a little bit of feedback there. Carlos, your technology relies on a gyrotron to create the millimeter waves. Two questions for that. Where is the power for that going to come from? And how is that going to look on the rig floor?
Right, so the gyrotrons are pretty mature technology. They've been around since the 50s, and they continue to evolve with fusion research. So at the surface, you plug the gyrotron to the electricity, right? And we're talking about 1 megawatt. This is not a problem for land rail operations. You have 3, 4, 5 megawatts on these rigs. So we basically pull electricity either from the onboard generators, diesel generators, or from the grid if you're connected to the grid. And we're talking about a 1 megawatt. The gyrotrons then made the millimeter waves at efficiencies in the range of 50 to 70% from electric to millimeter wave. That's why we picked them. On the rig floor, we want this to be a plug and play system for existing drilling systems. So if you imagine a conventional drilling system, a platform, we're going to have that to drill to basement rock. It's going to be a normal operation in the way it's done today. And once you're in the basement rock, you cement and case, you switch over. So you basically make an adaptation at the rig floor to switch from a mud-based system to an air drilling system in the same way that switch is done today. And we introduce the energy through the pipe, inside the pipe, right? So you'll see, you'll see the mud pumps here, and you'll see the equivalent compressors here, because that's what we use. You'll see the mud cleaning system here. You'll see the separators on the other side. And in our case in particular, you'll see a gyrotron on a container on the side, piping the energy all the way to the top of the pipe where it begins to go into the hole, and we beam the energy down. That's how we envision that. So we reuse most of the drill rig, actually. We just plug and play into the drill rig to switch to that operation.
Okay, and is there going to be specialized drill pipe needed?
No, we actually use our drill pipe is less like drill pipe. Drill pipe is thick-walled and heavy because you need to put a lot of torque and weight on the bit. In our case, we don't need to do that. So our drill pipe is a lot simpler. It's actually production tubing, standard API 5CT, 4.5, 5.5 inch tubing. So in that sense, the hook loads on the rig, the requirements for loading the string are much less because our drill string is much lighter, way lighter. And that's what we use as a waveguide. That's our conduit for the energy all the way down.
Okay, and I think I'd actually a question that would be interesting to hear from all of you, and that is, how does your technology affect rig floor operations? Why don't you just each weigh in there? Igor, you can get us started.
Yeah, thanks. So it's similar like previous question, our approach is to change as little as possible. Our ideal approach also for future is to have a dual rig or hybrid rig scenario when the initial part like conductor and the initial hundreds of meters will be drilled conventionally to start, and then once you are hitting the environment where you have the HPHT conditions or is a hard rock, then you just replace ideally replace the drill bit for the plasma bit. In our case, the preference is to use the cold tube type of the rig, where currently we have the one also that is already now in the preparation. We are doing that with NOV as a setup, and for the future also we are able to utilize the standard rig with the pipes, but we see a lot of advantages mostly when we are talking about 5+ kilometers to use the cold tube as a fast solution. Of course, today there are not so much practical solutions of the deep coal usage, but we see this as advantage. And the last point maybe to the surface part, that we are using also the energies that are typical in the rigs, like for example the power generators, diesel generators. Our prototypes, what we tested and in different facilities last 3 years, we're mostly consuming about 300 to 500 kilowatts.
Okay, excellent. Naveen, how about your technology?
What we envision within Orchid is there's not going to be any change on the rig surface because our system is completely or fully fluid driven. Our intensifier works by converting the mechanical energy or the vibrations into fluid energy, and the hammer tools provided by Drillstone Industries actually is fully fluid driven as well. So we can activate the hammering action and deactivate it just by using the fluid flow from the surface. So there's not going to be any changes in the or any conditions on the type of drilling rig that you might have to use. So we can use the same setup to drill through soft rocks and then activate the system for drilling through hard rocks and in basements. So that's the vision at Orchid.
Okay, and Mark, how about yourself? How's that going to look on the rig floor?
Yeah, so today with our 1 kilometer tool for both mineral exploration and for geothermal exploration, we use conventional dual pipe, which is called reverse circulation drilling. So we bring a central line where the projectiles and the compressed air and fuel all go down that single pipe. Similar to Igor, we have a future where you could use coiled tube. That's easy, but our real advantage is that in conventional, we simply will pump like balls those projectiles and fuel balls down without changing anything to what you're doing, except that you have a sequencer just after the mud pump where you're pushing those inert projectiles down to the bottom of the hole. Again, we are starting small. We're doing great things in the future, but right now we've got paying customers for our current high-speed exploration drills for geothermal and for mineral with a 2-pipe system. In the future, it'll be single pipe.
Okay, and let's stay with you, Mark, for a second on another question. What is the potential risk for overgauge holes using your drilling, and especially like in brittle rock?
That's not only a good question, that is like the question everyone asks us. And so in fact, that's what our field trials are demonstrating. What is unique about our system is that it is like a focused high mass laser beam. So you're firing a projectile directed energy into the rock where you're going. So there's actually very little lateral breakage. And what we've seen, and it was a perfect hole on the outer with what we call augmented hyper drilling, where the outer 10% is drilled with a regular bit. And so, but that bit is now 10 times more efficient. So you're getting the gauge hole that you want, your drill bit usage has dropped, and you're getting the speed and the lower cost. So it's a neat time for us where the field trials are showing not only are we going faster than prediction, but you're also getting all of that weight on the bit only on that outer ring. So you're able to get the rate, but you also get the gauge hole that you want. And that was really an important part of the field trials, is to prove that in brittle rock, it's hard, it's abrasive. We've tried it in sandstones, works great. We've tried it in everything from hard 200 plus megapascal granite to basalt to quartzite, and it all functions the same way. Makes a very good gauge hole.
Great. Okay, that's certainly important. Let's see here. This is a quick one for Naveen. but it's good to clarify this. Is the hammer portion of your tool also can it be used in drilling fluid, or is it just air?
No, it can be used by well with the drilling fluid. So we are going to test with pure water and water-based mud for this particular system or the prototype that we are developing right now. And we will also mix it with, as I said, some nanoparticles to avoid loss circulations. So this particular hammer system is completely fluid-driven, which is liquid-driven as well. So yeah, we can use it with water-based muds or any other drilling fluids.
Great. Okay, let's see. How about let's move over to testing. How are you going to test your different drilling technologies and try to recreate, hot rock downhole conditions? Let's see. I think Igor, why don't you get us started on that one?
Thanks. We already are in the process. Just like 5 years ago, we recognized we don't have any well around us that is 6-7 kilometers deep and we can come easily and test it. So I think the same problem of everybody in the panel. And that's why we then created quite a unique test facility in Central Europe near Bratislava, when we developed several places, including one what we are quite proud of is a high pressure, high temperature facility, when we can create high temperatures, but mostly the pressures that are more than 12,000 psi in a pressure. And it took us some 3 years to develop it, and then we were making the continuous testing in that facility to be able to recognize all the processes that behaves quite differently in such HPHT conditions as in atmospheric. And this was backed also not only by the private investors and operators that we are working with, but also we were able to win several grants in the European Union to help us with the infrastructure, as it is quite costly. And now in the next stages, we are now moving from this facility testing and some shallow well testing that we have also our cold tube rig there to the customers field. It was a little bit slowed down by COVID last year as it was lockdown and so on, as we have the agreed field test with Mall Group, one of our investor. But fully believe that this year and next year will be much better in that, and we can move then to the customers or partners well, and first the facility and then well to test the whole system.
Great. Yeah, that sounds really interesting. Naveen, I think you guys also have a interesting test center.
Yeah, that is true, Jody. So I think I would say that our testing procedure is about threefold. First one is to understand the jetting process to create the grooves or the slots in different type of rock candidates. So we have an experimental setup in France where we try to recreate the downhole conditions and use different type of nozzles to understand how that particular fluid is creating the grooves in different rocks, right? So that's the first step. And the second one is to convert the actual vibrations of drill string to the fluid pressure. So that's carried out by our partner in China. They have an experimental facility to check this particular process. We have achieved about a conversion rate of about 150 megapascals of output fluid pressure through the nozzles. But during the project, we expect it to increase up to, let's say, 250 megapascals so that we can create those necessary pressure to create the grooves in hard rocks. And the third step is to combine this jetting and the hammering process. So we are redesigning the hammer bit and the hammer itself in order to combine that with the high pressure nozzles. And we have experimental facility to run different BHA configurations in both vertical wells and horizontal test beds in France. So that'll be the third step to see what is the increment in ROP that we would receive because of this prototype. And then finally, by the end of the project, we expect drill stars to actually go for a field trial depending on the operations around the globe. So I would say this is the different steps that we are taking. For now, we are only at a stage where we're going to test the different nozzle combinations or configurations to create the grooving process for stress relief in deep hard rocks, let's say.
Okay. I have another good one from the audience, and that is, where are each of you currently being funded from, and how much additional funding will you need to commercialize your drilling tool? Why don't we start with Carlos?
All right, so we have an ARPA grant from the Department of Energy, and we have venture money. We're talking about $11 million total. That's what we're operating with. And we are currently fundraising. I mentioned before, we're going to be taking this into the field over the next 3 years, which means a lot of systems engineering and integration with drill rigs. So we are currently fundraising a round for that. If you're interested, talk to me, please. We're actively in that process. Waze does not aspire to be a drilling company. It aspires to be an energy company. So when I get asked the question of how much to commercialize the drilling technology, well, we're not going to commercialize the drilling technology to the open markets. We're going to use it to then gain a competitive advantage to develop geothermal fields and produce energy. That full envelope requires drilling, completion, stimulation, surface systems, power plants. So you're talking about hundreds of millions of dollars. A lot of that money, though, doesn't need to come from venture capital. A lot of that starts to become money that's viable via loan guarantees or project financing. So the better question is, how much money do we need to show that the technology works in the field and can scale up to the 20 to 500 kilometers that we always talk about? I think that's a $50 million journey.
And how long do you see that taking?
3 years. That's the plan. We're raising $50 million for the next 3 years to show exactly that.
Okay. Igor, how about yourself? How are you guys funded, and how much funding do you need to go commercial, and how long do you think that'll take?
Yeah, in different phases of the company, there was also different way of funding. Initial phases mostly, of course, by seed money, by shareholders, and also we were quite successful in winning several grants that help us to build the infrastructure. So public funding mostly from the European Union. Then in some 5 years ago, when we moved to more commercial, let's say, or the more commercial trajectory of the company, we start to raise the money in the Series A from the venture capital companies, but also from the industry, mostly from the operators and also drilling companies that were part of our joint industry project. And now last 3 years, our main focus is first of all to the industry, to the users, operators, and their venture arms. And for the next phase, what will be the testing and then the pilot project is also the focus for the project companies that definitely can bring then the project financing into the concrete pilot. But also in this way, it's a combination still with some public funding that is always very helpful. Like we win also the projects, for example, in UK, in our branch, what we have in Bristol. And of course, we are applying more now in Europe and maybe also in the US for this Green Deal funding that will be. But last but not least, now our main focus is for in the current investment round that we are now fundraising to get enough funding in a size of about 20 million to bring the whole system to the field with the drilling companies and with the financial investors that will back up all the process.
Okay, great. Mark, same questions to you.
Oh, sure. Hypersciences is a vertically oriented platform technology company. We actually have 3 verticals. We have the drilling for geothermal and exploration. We have tunneling and mining, and we have aerospace. We were one of the world's largest crowd-funded companies back in 2019. On our Series A, we did a Regulation A. We raised over $13 million between seed and 10 million in the Regulation A, which is basically you go mini public. So our next approach right now, the drilling is going well. We actually are self-sustainable to build with customers that tool for the 1 kilometer. If we want to accelerate that, which we do, the tool development for a deep geothermal drill is actually on the order of magnitude Carlos and others have talked about. We're actually in our Series B. If you heard our pitch a few days ago with Richard Branson yesterday, we are raising 70 million on a Series B. Some of that will be through a regulation aid crowd financing. So that's how we do it. But again, our tunneling, the phone's ringing off the hook because of our tunneling and micro tunneling. We actually consider the long-term future of our funding for geothermal and in tunneling to micro tunnel for geothermal, micro tunnel for access for mines as well as transportation businesses. The aerospace technology will be flying up to, we call the Branson line, 85 kilometers with our hypersonic 4-inch system. So coming up soon, this verticals that we're after each need enough capital, but that 70 million over the Series B will cover and create sustainable businesses in each one of the verticals. So pretty exciting time for hypersonics for us.
Yeah, it sounds like it. Naveen, how about Orchid? How is it funded?
Sure. So Orchid is funded by the European Union under a program called Horizon 2020. So we have a grant of about 4 million euros for 3 years period. The goal for this particular project is to increase the technology readiness level from 2 to 3 to, let's say, 5 to 6. So that's the scale that we are looking at. And over a period of time, over a period of 3 years, we are expecting to go to about TRL of 6. And our industrial partner, Drillstar, is actually an established company. We are slightly different from a startup ecosystem. They already have customers and are self-sustaining. So we expect that the commercialization would be relatively faster. Once we have this technology or the prototype ready in the next 3 years, then they would provide us with the platform to go for field trials. And what would be left is to only optimize the parameters and test what would happen as a normal feedback from any field trial. So I would say that it would be relatively inexpensive to move to a commercialization aspect with this particular project.
All right, thank you. Let's move to a little bit more of a higher level question now. And that is, where do you see your particular technology fitting in with the geothermal industry? And that could be, what kind of holes do you think you're going to be drilling? What kind of depth? What kind of temperature? Are these going to be for conventional geothermal, hydrothermal, EGS, closed loop, that sort of thing? Does anybody want to get us kicked off?
Sure.
Go ahead. Go ahead, Mark.
Okay. So our models, geothermal, doesn't matter how people want to do it, right? We're agnostic to the plant. If somebody wants a hole, we'll help them make it. We'll license our tools, whatever it takes to make hole, to make energy available to the masses. So our goal is early, start with near surface, the 1 kilometer. If there's hot, wet rocks near the surface, fine. We will lower your cost. As we grow in the technology, we'll go deeper. Great things start from little beginnings, and we're good with the 5-inch hole exploration drill that we have, and then grow it into, we believe, half-meter size, we'll call it micro tunnels for geothermal. And we're currently on the surface and a depth, meaning kilometer or so, able to make holes, micro tunnels, at 20x the rate that can be made today, again, near the surface. But that type of technology, when you start going deeper, we're looking at 200 degrees C plus in the future, and tunnels that are sizable enough to create the volumes. In order to get energy anywhere with geothermal, you need long, deep, 5-kilometer depth. You need to go laterally another 5, and you need to bring it up if you believe in the closed loop solutions. You have to solve the drilling cost. You have to solve the completing costs. And, we'll let anyone decide what plant they want to put in. I'm happy to help. We are looking for partners to demonstrate the technology as we continue to march down in depth. But to start with, we're making small or big micro tunnels near the surface, and then grow the technology into those deep depths. So That's our strategy, and we're again looking for partners and in pilot holes around the world.
I'll go next.
Oh, go ahead, Carlos. Yeah.
Okay, I'll go. So I'll be brief. So for quays, we talk about supercritical geothermal. In reality, terawatt geothermal means hot geothermal. So it's more about the temperature. The depth is just a consequence of the geothermal gradient. So we always talk about 500 degrees C, but you don't start there. You start, 300 plus. That's where we want to be. The ultimate goal for us is to go to market through geothermal so power dense that you can actually repower power plants. You can go to a coal plant or a gas plant, and you can leave everything in place minus the boiler and simply feed geothermal steam to the turbine. So for that, you need 300 to 500 degrees Celsius. And that translates, depends where you are, it translates to 5 kilometers to 20 kilometers. That's where our specification comes from. Like Mark, we start with shallower holes. I think there's some workflows in mining exploration that lends themselves well to the technology we have. So we'll clearly explore market revenues that way. But for geothermal, we want to go to hot, dry rock at 300 to 500 degrees C anywhere in the world.
Yep. I agree with both predecessors, also Carlos and Mark, because they describe very well that I think the new drilling technology, if successful, it should work for anybody, like even for closed, for open loops. Of course, the challenge is, as was correctly mentioned by closed loops, that even they need much more such a new drilling technology, because otherwise their cost will be very high. And our clear market where we see also our plasma bead is where the curve of the growth of the cost per meter is starting to grow significantly in high pressure, high temperature. We want to keep them constant or linear, and from some 3-4 kilometers, that is typical depth, and we are reaching some harder conditions, then to drill to whatever. So of course it will not happen in the first year that you can drill to 15 or 10 kilometers. Our first focus in the first project is to 5-6 kilometers, when we will be able to bring the value, even extending the current, let's say, conventional market in 1 or 2 kilometers plus as a feasible depth, and then to go step by step, kilometer after kilometer. Here the point is that it is not so dependent on the tool itself, it's dependent on the infrastructure. So here is, I think, absolutely great chance for the oil and gas and drilling industry to convert part of their assets or experience into something that can move drilling for the clean energy, not only for the fossil fuels.
Yeah, I agree. Well, our time is coming to a close here. It's gone by really quickly. I think we have time for one more question, and I think this is one that I want to hit because it's important to a lot of people in our audience, and that is, what skills do you guys look for when you're making new hires? What kind of roles are you hiring for? Anybody want to start that one off?
I'll go.
Go for it.
So we're very early in technology development. So it's a very technology heavy company right now. We're looking for engineers, mechanical, electrical. We have nuclear engineers, signal processing control engineers. But over the next 3 years, as we go to the field, we start getting a lot more into field operations, managing a site with a drilling job. And geoscience becomes relevant, geology becomes relevant, drilling engineering from the oil and gas industry becomes relevant, completions becomes relevant, but right now, pretty technical, for the time being, going into 3 years, starts to get more into the operations side.
Yeah. Here maybe add to that definitely we are not looking for conservative people, because our employees, they should imagine some different world a little bit in the drilling as the standard drilling world is till now. So definitely what should be, except of course, or in addition to some professional level that should be on a high position, it is some grit and some entrepreneurial spirit that they are able to really to make the big changes in the whole industry, and they are ready even to go several years through some very hard environment, and maybe not too much people are believing to them, but they are able to go through that and prove that in the end they are successful.
All right. I think we do have time for another question. And this is a kind of quick one, and that is, will directional drilling be possible with your drilling technology?
So I'll go first on this one, Jody. So Hypersciences developed a drill with Shell to do 15 degrees per 100 with the tool. So the ability to go lateral, particularly in geothermal, with the new opportunities in EGS and AGS, closed loop solutions, requires you to go down, over, and back up. And so that's a key piece to package all this. We spent years, and you asked, who are the engineers that we need? We actually need, the rocket science is done. All of that works. It's just packaging it all down whole. And there are so many brilliant mechanical engineers down out of Houston and other parts of the world where they know how to make all this stuff, these awesome pieces of, I call Swiss watches, work super reliably underground. And that's what everybody wants. They want a drill that's reliable. And, that's where we're spending our time is developing the real, bits and pieces, so a roughneck can just run this thing and not have to think too much about the rocket sciences that's designed it in there.
Naveen?
Yeah, sure. So yeah, we can go for both vertical and the laterals. We have an experiment set up in France, the same one that I've been talking about. So we have the capability to test this prototype for both vertical and horizontal profiles. And to answer one of the previous questions here, I agree with all of the panelists. Our technology is basically to increase ROP of any hard rock section, so either shallow or deep. So irrespective of any type of geothermal systems, we aim at increasing the ROP by at least 3 times and bring down the drilling cost in hard rock sections by about 65%. So in one of the case studies of the economic model that we did for a particular EGS system, we expect a reduction of about 30% in total construction costs. So that's the goal for Rocket.
Okay.
Shortly, just practical output of our also testing that we did also last year for another application like decommissioning that for example, we tested under 30% incline, 30 degrees inclined. Basically, plasma bed is not gravity dependent, so even it can go upside down. And I think here the biggest issue for everybody will be, again, not the tool itself, but the removal of the particles and so on. So this is something that will be different in horizontal. And our first priority is, of course, the deep vertical wells.
Okay, and Carlos?
Vertical, right? The oil industry made plenty of oil before it ever went horizontal, right? You go for temperature, it's down. It's not sideways, it's down, right? So we don't focus on directional drilling. I know a lot of people in sedimentary geothermal want to do that because you want to frack, you want to create these very complex, very lengthy completions. But for us, we're going to go down, seek the temperature, down, straight.
Okay. Well, we are at our 5-minute warning. So I'm going to throw it to each of you for a minute of closing thoughts. Let's start with Carlos.
What's the question, Jody?
Just so closing thoughts.
Closing thoughts. Okay, let's be ambitious about geothermal, right? I used to work in the oil and gas industry. That company works in the terawatts, We need to be working in terawatts. That's the potential of geothermal. I am not happy with gigawatts. I'm not happy with projections of geothermal going to, 50 gigawatts by 2050. Forget that. We can go to 5, 6, 7 terawatts everywhere. You need to drill deep. That's why we're doing this, right? So to me, this is a life mission. This is a passion. That's what we need to do. And we cannot let on that ambition.
Okay, Igor.
Yeah. I think what is now a unique opportunity absolutely for the whole drilling oil and gas industry in this time of the converting from the fossil fuels to something new is to utilize all the skills experience in this big transition. And I think combining of the skills and abilities from other industries, as most of our employees are coming, automotive, some physics and so on, to put together all the advanced technologies and combining it with this big assets experience is something that can really make a huge change in the next 5 to 10 years. And I absolutely agree that today's geothermal market and potential is totally underestimated, not only going for the public governments, but also in the private sector. And it should be much more much more louder to be heard from our community that it is possible to make it differently and to make the geothermal anywhere simple, because you can have clean baseload energy source almost anywhere, and it's just a question of technology enabler.
Yeah, for sure, for sure. Mark.
Mark Russell, Hyper Sciences, and what we presented today and have done over the past few years is show that we have a mature, novel way of breaking rock in a fundamentally new way, and we're bringing energy to the bottom of a hole so that we can open up fast. And really, it's about low-cost drilling and access to these energy resources. We think we need to be hyper incremental about this. And it needs to be a sustainable business where you're starting simple, firing these projectiles every few seconds, opening up new micro tunneling, creating good business revenue, and also creating a drill that in the future will be this workhorse of technology for deep geothermal. But people, when you bring new technology, new but familiar, and that's where I think all of us have said, look, we don't change the game too much for how you operate. It's you're operating in a new way. And that's what we're trying to do with our customers. So by all means, become a partner with us to learn how to drill and join the path. Thank you, Jody, and thank you, Pivot 2021. It's been awesome to bring hypersonic technology to view.
Thanks, Mark. And Naveen, close it out.
So what I think is, among all the panelists on the technology, what I see is that there's a huge interdisciplinary approach between different technologies from one industry to the other, and also among different organizations. So Arcade is something, what we focus on is the transition between our interdisciplinary approach between academia and the industry partner. So we have a great team working on different type of technology to improve drilling process. And don't forget to follow us on Twitter and LinkedIn. You can visit our website, arcade.eu. And if you want to know more about drilling dynamics and some other approaches of digital twins, then feel free to talk to me over LinkedIn and so forth. So thank you so much for the opportunity. And I think Pivot is doing a great job in this transition from oil and gas to geothermal energy.
Thank you, Naveen. Well, that brings our panel to a close. I'd like to thank everybody for watching. I'd like to really thank Jamie and the whole Pivot 2021 crew for putting this together. It's really a fantastic, group of panels. And I know for this panel, considering my past as a drilling engineer, it's super interesting to me. I think there's in the near term, there's a lot of potential for PDC and those kinds of improvements, but long term, these super deep and super hot rock, we're going to need innovators like this to get us there and to make it economical. So I really appreciate the panelists joining us. This is really interesting technology, and I look forward to seeing how it goes. So again, thanks to everyone. Thanks to everyone watching, and we'll see you at the next session.
Thanks, everybody. And yes, thanks.
Bye.
Thanks, Jody. Thanks, Pivot. Cheers.